So this is exploCFD, very simple GUI. I'm going to import a simple PDF that came out of the actual investigation report. And to do that, I just click on this button here, which is load file. So I'm going to go load file. In drawings is set up, you'll find heaps of drawings, and I'm looking for Buncefield plot plan. And literally, it is a PDF that is taken out of the Buncefield report. Once you see not processed, you can click on it and you can see the drawing. Here is our site. This is the 3 tanks, 1, 2, 3. Here's 3 Cherry Trees Lane, which is, we agreed, has a lot more than 3 cherry trees. And this is Buncefield Lane, which is the street adjacent to the Fuji building, which was destroyed in that building here. So what I want to do is I want to remove a lot of this junk now. There's a lot of stuff that is sitting in this drawing that will be treated as walls that shouldn't be treated as walls. For example, the boundary here. We need to get rid of that. The lines demarcating the street, Buncefield Lane and 3 Cherry Trees Lane. So the way to do that, first of all, you could zoom in and out by rolling your middle mouse button. I hope, you know, the younger generation, they use the mouse pad. I don't know how to do it on a mouse pad, to be honest. But if you have a mouse, and I recommend that you do have a mouse if you're using exploCFD, your middle mouse button allows you to zoom in and out. And I'm zooming out, and I'm going to hold down now my right button, my mouse button, and I'm going to draw a rectangle. Select the rectangle from the top left to the bottom right. I'm going to select everything that is I'm going to select that red triangle, the red square, and everything inside it by doing this. So I've just released the right mouse button, and you can see everything turned red. That means everything's been selected. And then I can go anywhere, and I can right-click again, and I've got this menu, and I'm going to say exclude selected lines. Okay, so exclude selected lines. And everything's gone purple now, which means that the software is ignoring all the lines. So I have to go back now and tell it to include, for example, the Fuji building. So I can select the lines that are that represent the Fuji building and include them. This is slightly tedious, and I'm going to show you how to do it quickly for this case. But it's tedious. It's nowhere near as tedious as drawing the whole thing from scratch, which is what you would do for a software like Flex, like that. If I've selected too much, which I have here, for example, you could see that I've selected this bit here. By the way, you can pan with your left mouse button. I can hold down the Alt button and select something, and it will deselect it. Basically, while holding down the Alt button, you select something, and it deselects whatever you've selected. And so now I've got the Fuji building selected. I certainly don't want boundary in boundary way to be selected. So you just select, again, with holding down the Alt button, you could deselect everything. And now I've got the clear outline of that Fuji building. I can right click anywhere, and I could say include selected lines. So now it's gone black. So this is going to be treated like walls. I could do the same with my tanks, right? This is one of the tanks, that top tank, that second tank, that third tank. So I've selected them by holding down the right mouse button and selecting a rectangle that includes these 3 circles. And once I'm done, I release the mouse and I go include, and these go black. So now I've got 1 building and 3 tanks. And you could go on and on and on and include this North Gate building, I think it's called this. You can select it and include that. You can include this building by selecting it and including it. Okay, so hopefully you've been able to at least do 1 or 2 of these structures, selecting them and including them. You could, if you've selected something that you don't like and included it already, it's easy. Let's say I've selected this, I've included it. It's gone black. I don't like that. I changed my mind. I just simply go back and select it again and exclude it. Yeah. So this is kind of like what I need. These are the salient features of the model that I need. I need the three tanks. I need the buildings, because after all, that's what we need from this explosion model, is the pressure on the Fuji building. That's going to be our metric for the performance of the CFD model, and a couple of other structures just to see the interaction on them. If you haven't got time to do this, or if today you haven't been able to keep up with me, I'll show you another thing that you could do. You could always save everything, and I have, and you should have this in your folders. I'll show you how to do it. I'll go back and I'll exclude everything here. I'll go exclude, and then I'll go and load. I'll click on the name of the drawing, and I'll go load setup, and I need to load the Buncefield ECF file, and that's just got the whole setup. And I've just loaded it. Okay, so what it's done is it's taken all the things that I've done in the past. You can see I've selected some buildings here. They're black. The rest is all purple. The three tanks, the other tanks that are in the tank farm, which is what it was. This is the emergency pump house, by the way. And another, I think this was like a gatehouse. I've selected the important features and I've saved them. I've also, you can see here, I've put the gas cloud across Buncefield Lane, only Buncefield Lane. I'm going to put the appropriate congestion in there so that we're able to run the simulation. By the way, to put in the gas cloud, you could just right click and go custom cloud and select the gas cloud, and just make sure, this is important, make sure you press escape once after you've done the gas cloud selection. And there's videos online of this process. I'm sure that those of you who have tried running the simulation, the simple simulation that we've had, will have come across this. But if not, you can always contact us and or look on our YouTube channel online, where it's got plenty of examples where we have taken care of this issue. Okay, so you can see that it's got the right mass. If you don't have the right mass, you could change the fuel mass to 2537. Remember, we calculated it when we're doing that MEM calculation. So 2537 is our estimate. By the way, these are estimates. As I said, you have to keep in mind that all these processes, no matter how accurate that they are compared to other methods, this might be more accurate than multi-energy method or TNT equivalence. It's still an estimate. So this is an important parameter, 2537. If you have 2,500, that's good enough. This is a very important parameter, the pipe diameter. Now, this is the average diameter of the obstruction of the pipe in cross flow in the cloud, right? So in Buncefield Lane. So it's the average, in this case, it happens to be the average diameter of a branch of the tree, of the trees in Buncefield Lane. And VBR, maybe change that to 0.55. Typically, it's very difficult to do explosions with benzene, and typically what people do in industries run propane instead. They're fairly close in terms of energetic release, especially if benzene has to be a gas cloud to it's got to evaporate first. So if you take that part out, the ignition of a benzene gas cloud and a propane gas cloud, they're ballpark similar, let's say. Okay, so these are the important parameters. So you want to press 100% in methane, in propane, and 0 in methane, which is the default. This should already be in there if you've loaded the file. You've got 2,537 kilograms, which we calculated. you've got an average pipe diameter, an average branch diameter of 0.05, and you've got 0.55. And the rest, the confinement is about 0.4, just leave it, maybe 0.35 might be between 0.35 to 0.6. You know, some things in accident investigations are entirely unknowable. So you've got to do the sort of range and get a range of conditions. But that's basically what you need to do to run this simulation. I'm going to use a very large time step, which is not very accurate, but we don't have a lot of time. So I'm going to cut this down to that, maybe run 1,000 iterations and output every 50 iterations. I think that's all we need. We've put in the drawing dimensions that came in with the software, with the ECF file for the software. Has anybody actually managed to keep up with me here in this case? Anybody doing it at home while we speak on the chat? Okay, so you could always do this. Oh yeah, all right. That is either Vivi. That's Vivi. Yeah, Vivi. Well done, Vivi. Well done. Okay. I'm sure there's others I can't see, but well done. And some of you have actually done the cases. Well done. All right. So what we're going to do, I've got a millisecond of a time step. I've got 1,000 iterations, 50 time steps, output every 50 time steps. Just perform analysis, and you should see it processing. And within about 15 minutes, even less, you're going to see some results, and we're going to see the explosion that propagated from Buncefield Lane. In the meantime, let's continue with this presentation. I'll show you some cases. Actually, here's the kind of results that you should expect, right? So this is a Buncefield case. So if you could see my presentation here now, you could see the explosion propagating outwards. You should be able to see this on your computer if you run this, and the shock wave reflecting off first the North Gate and then now the Fuji building, and of course off the tanks, and you could see pressures in excess of 4 bar. So you remember we calculated 2.5 bar using the multi-energy method. It is about 4 bar here, and with other CFD models it was about that number as well. So that's the Buncefield case. And while our case is running, I can show you some other things. This is the Beirut model. This is, of course, was it last year or was it 2020? 2 years ago? I can't remember now if it was I think it was last year. There was a massive explosion in Beirut. That was an ammonium nitrate explosion. That ammonium nitrate explosion occurred in the port of Beirut. It was, I think, huge amount. I think 20,000 tons or something that were sitting in a port and in a warehouse in a port, and they ignited and caused widespread damage, killed quite a few people. Most of the people who died didn't die from the strength of the explosion. The explosion was very severe in this region here. This is the sort of industrial port area. The pressures here were very high. And this street, if you've ever been to Beirut, it actually divides this industrial port area from a very sort of high-end place. It's like the Mayfair of Beirut, if you like. So it's quite an expensive area. And across that street were a lot of the fatalities, and also on the street itself, mostly from shrapnel, right? So you didn't get buildings that were decimated and landed, and the pressure. It wasn't the pressure; it was shrapnel and structural damage that caused this. But we ran this case. We got so the main question here, of course, is I think it was 2,700 tons of ammonium nitrate that was sitting in the warehouse. And ammonium nitrate's notorious for not all going off at once. So it'll go off if you watch videos of this explosion, you'll see that it was building up. The event was building up. So it progressively got worse and worse and worse, and then finally the Big Bang came. So the question was, how much of the 2,750 um, tons was consumed in that Big Bang that takes place? And so one of the things that as an excellent investigator you could do with explosions is you could look at the size of the crater that's left behind from that explosion, the size of that crater. And there are geological relations that tie the amount of explosive that was available to the size of that crater. And so the crater was, from memory, about 180 meters in diameter, and it was like 40 meters deep. And so this corresponded to only about 100 and something tons of ammonium nitrate. So the amount that went off in the Big Bang, so there were several bangs before, but the amount, and several bangs after, but the amount that went off in the Big Bang was a small fraction of that 2,750 tons, according to our calculations, based on the size of the crater. And when you run 140 tons on exploCFD, you see a pattern that kind of corresponds with massive damage in this area and broken windows and shrapnel, deadly shrapnel, nevertheless, beyond the Charles Hello Street. And that's basically what was seen in real life. And it was a very powerful explosion. Again, this was a detonation. It was a different type of explosion. It wasn't like Buncefield. It wasn't a gas explosion. Of course, it was ammonium nitrate. By the way, ammonium nitrate is difficult to ignite because it's in, and that this ammonium nitrate was, I don't know if this is something to be proud of, but this ammonium nitrate was actually made in Australia by a company called Orica. And it comes in a form called prill. And prill is it's like a desensitizing agent around this ammonium nitrate. And so that's why it's quite difficult to ignite. You need a sustained heat source to get it going. And then once it gets going, the energy from the ammonium nitrate itself will start to build up. And if you watch videos of the event, that's basically what happened. So so this does point to like a sustained heat source. They said there was welding, and then they said there was a lot of politics around the story. This is what's known as a BLEVE. So a BLEVE is basically a sudden release of liquid that is below into a lower pressure and higher temperature atmosphere. Okay, so liquid nitrogen, if you spill it, it will immediately evaporate and cause a massive rise in pressure. And these things can be very, very dangerous as well. So this is a BLEVE, and you can see here, these are a set of offices. This was done for a client in the Middle East. I think this was in the Emirates. And you could see that, well, if I could get it going. Everybody hopefully can see my screen now, right? So you could see the pressure waves propagating out of that tank and impinging on the first set of offices. But that set of offices actually acts as a shield, partially, only partially, to the second set of offices that still experiences pressure, but far less pressure than first row. So the first row kind of protects the second row. And then there's one. This was in Brazil. This was in the south of Brazil, in a place called Rio Grande do Sul. Rio Grande do Sul is the southernmost state of Brazil. It's where Luis Suarez is playing right now. If you're following this sort of thing, that team Grêmio, that's in Rio Grande do Sul, this was a floating storage and regasification unit that was off the coast of Rio Grande do Sul, next to a sort of a highly condensed area. It's a favela, really, called Vila Mangueira. And if you do the calculations using MEM or GAME or FAST, which is software that relies on these, you get overpressures here would kill everyone. And obviously, you know, there's two options when you use MEM. You could either be conservative, and that's the smart thing to do, but it's also a very expensive thing to do, or you could be under conservative, and if you're wrong, then you know it's disastrous. And so again, this was one of the cases. I think this case is actually a video on YouTube that we take you through the whole case, and you can see the explosion taking place. The overpressures at Vila Mangueira are quite low. And we continually do validation cases, compare with experiments. This is one set of experiments here. Validation is very important in these cases because, as I said, there's a lot of uncertainty in all of the CFD. And there's a lot of uncertainty in the experiments as well. So, but at least if you get two things to agree with each other, chances are that you're less wrong than if everybody disagrees with you. Although that's a dangerous way to think. But you know, when you're running blind down an alleyway, you need any sort of light that you can get. Finally, it's not just and by the way, we're about 390, about 400, maybe 40% of the way. We could see the explosion. We could look at the explosion after this next slide. I'm going to show you another thing. We said that the turbulence from pipes and cross flow can cause instabilities and flames that increase the speed of the flame, which results in higher overpressure. But it's not just that. There's a whole series of instabilities, Raleigh-Taylor instabilities, and one interesting one here, and this comes from an experiment in École Centrale, is the effect of sound. Just sound can affect the flame. And I won't show you the whole thing, but this guy basically has a flame and is looking at it with like a Schlieren type image, and the Schlieren image shows density gradient, right? And then he tries to so let's see here. So you could see okay, so we'll see. Yeah, so you could see the effect of sound. This is the effect of that sound that you're listening to on the flame. And you'll see as he changes the frequency, that's 300 here, it changes the density gradient just due to pure acoustic waves. So it's not just so so now he's going to play bass to it and show you the effect of that bass sound on the flame. Yeah, so that's basically one of the other instabilities that can affect flames and can cause a change from a deflagration to a detonation, can contribute to that. But by far the worst one is the one we talk most of the time about, which is turbulent flame acceleration. Okay, so we're about halfway through that simulation. And what I'm going to do is I'm going to just show you some of the results that have come out so far, because you can look at the results as the thing calculates. So let's see. So I'm going to start up this ParaView. ParaView is the viewer that we use, a very powerful viewer, and we're going to have a look at these results. How much time have we got in the 40 minutes, Rob?
I don't know. There's no real timer. It just tells me that there's 5 minutes left, and it hasn't told me that yet. So, but I think,
okay.
There we go. The time left is 10 minutes.
Okay, good. All right. Well, we hopefully will be done until, we've only got 10 minutes anyway. We've got 11 minutes, so
Correct.
worked out beautifully. Okay, so I'm gonna load the presentation. Sorry, I'm gonna load the results here.
Recording in.
So, hello?
Yeah, I'm here.
Okay, so I got, yeah, okay. No, I thought somebody was asking a question. So I'm gonna load some of the results. So we've got quite a few results. It's not complete, but here's what we have. And so this is the domain. I'm just going to flip it around because it's always upside down. This is here the Fuji building, if you remember. This is the Northgate building. These are 3 tanks. You can't see yet the gas cloud, but if you click on this macro here, all it does is it takes the overpressure and subtracts atmospheric pressure from it. If you don't see that button, you could just open macros and import new macro, and it should be in the macros folder, overpressure it's called. And if I go here, you could see the start of that explosion. So these are the results that we just ran. This is the beginning of the explosion. I could change the color scheme here to apply, and I can run this case, and you can see a reflection of these buildings. And if I wanted to take a look at the Fuji building in detail, I could go add plot over line. And just make sure that, you know, so I don't know if this came across. One of the consequences of using of this large uncertainty in CFD that we are finally sort of taking ownership of is you need to be a little bit more conservative. And if you're going to do that, you might as well speed up the process. And the way that we've decided to do that is instead of running a 3-dimensional calculation, we run a 2-dimensional calculation. It's faster because this would take a week on this computer if it was a 3-dimensional model. And it is within the same uncertainty range because of all the uncertainties we spoke about, right? So, so I'm going to plot overpressure over time. Actually, it's going to plot everything. I'm just going to remove this. And then you can see a whole bunch of items here. I'm just interested in overpressure. And so overpressure along this line. So this is X coordinate here and Y and overpressure on the y-axis. And if I zoom back, you could see I can just not use a custom range for either. And if I zoom back, you could see the pressure is minimal, 2 pascals, nothing. Yeah. But if I cycle through, it starts as it approaches, the pressure starts to rise, and then we are talking at about 190,000, 2 bar here. Now 2.25 bar, 4 bar at this point, and then it starts to drop off again as the shock wave is being reflected off the Fuji building. So I think we reached 4 bar, and then it starts to drop off again. And notice how you could see shock reflections off these buildings. This is where initially the explosion converts the chemical energy into potential, which is pressure, and thermal energy. And as it expands, that potential thermal energy becomes kinetic energy, becomes velocity. But when the flow hits a wall, the flow is stagnated, and that's converted back into that kinetic energy, that velocity is converted back into overpressure and temperature, and that's called the stagnation pressure and temperature, and that's what you're seeing here. That's the process whereby the reflection is taking place off this wall. And if I if I go and I plot over time, so now I'm looking at the average overpressure over time. So I could zoom out, and that's your overpressure. That's your classic triangular shape that you're seeing. So this is the absolute maximum. This is the 75th percentile, the average 25th percentile, and so on. So we are at about 4 bar at this case, but 2.5 bar wasn't bad for a quick hand calculation, and so it's a reasonable estimate given that it was a back of the envelope calculation. I think that wraps up my presentation. I hope everybody was able to follow